Hi everybody, welcome back to the Feynman technique. So today we're going to be developing a closed form expression for this integral right here. U substitution and integration by parts are not going to be of much use in this problem. So instead we're going to use Feynman integration or differentiation under the integral sign. All right. So the first thing we're going to do is we're going to treat that constant inside the logarithm here as a variable parameter t. So basically, we're just defining it as a function of t. So the first thing we're going to do to develop this closed form expression for I of t is differentiation under the integral sign. So we're going to differentiate I of t with respect to t. And the Leibniz rule says that we can move the derivative operator inside the integral sign. And we need to change it to a partial. So we just move this derivative right inside the integral as a partial derivative. All right, and then we evaluate the partial derivative. So the partial derivative of that is going to be this. Okay. So this is our I prime of t. And this integral can actually be evaluated using partial fraction decomposition and integration. Actually, just partial fraction decomposition. So we can perform partial fraction decomposition on this. It's a little bit complicated, but if you do it and then do the algebra, simplify it, this is what you get. So this fraction decomposes into this expression right here. So our I prime of t is actually equal to the integral from 0 to infinity of this with respect to x, right? Our I prime of t was this with respect to x. And that evaluates to this. If we take the antiderivative, we're going to get arctangent x and 1 over t arctangent tx, respectively, for these two antiderivatives. And then we evaluate at the bounds. You'll notice at infinity, this becomes pi over 2, and this will become pi over 2t. And at 0, both of them go away. So there's a lot of algebra you have to do, a lot of simplification, but ultimately it simplifies to pi over 1 plus t. So that is our I prime of t. Now, to get back to I of t, we anti-differentiate our I prime of t. And that's a very easy integral to do. That's just pi natural log of 1 plus t plus c. Now we need to figure out our constant of integration. We can do that by realizing that I of 0 is equal to 0. You'll notice this is our I of t, and if we plug in 0 for t, the whole integral goes to 0. So we can determine from that that c has to be equal to 0, since our I of t was pi natural log of 1 plus t plus c. c is 0. So our final expression is pi natural log of 1 plus t. All right, guys, hope you enjoy that, and we'll see you next time.